I want to introduce you to a very special number in the world of mathematics, Euler's number. Notice that it is pronounced Euler, not Euler. Because it is a very important mathematician's name, I expect you to pronounce it as correctly as is possible in English and say Euler. Relatively speaking, in the world of mathematics, this number was discovered only recently, resulting from various explorations in calculus during the 17th and 18th centuries. Let's begin with another very famous number. At least as far back as 3,600 to 4,000 years ago, the ancient Egyptians and Babylonians were exploring the concept of how the circumference of a circle relates to its diameter. Specifically, they knew that the ratio of circumference to diameter is one set number, regardless of the size of the circle. We now know that ratio is pi, and we now know it is an irrational number. However, it took mathematicians thousands of years to get a handle on the nature of this number and how to calculate increasingly accurate approximations for it. Some of the most notable advances regarding pi occurred in ancient Greece with work done by Archimedes in the 3rd century BCE, and in China with work done by Liu Hui in the 3rd century CE. Pi was critical for many formulas in geometry, particularly those associated with conic sections, such as circles and ellipses. There were, of course, other important numbers in geometry, dealing with the square roots of numbers that were not perfect squares. For example, in an equilateral triangle whose side lengths are 2, the height of the triangle would be the square root of 3. And the diagonal of a unit square has a length of the square root of 2. Mathematicians really struggled with these numbers that could not be written as a fraction or ratio of integers. We now know them to be what are called irrational numbers, meaning not a ratio. As the ideas surrounding calculus were being discovered in the 16 and 1700s, another unique irrational number started to surface. One application involving this number comes from the concept of compound interest in finance. Before calculating interest after one period of time, we must first divide the interest rate R by the number of times per year that the interest is compounded, which is K in this formula. We then iteratively calculate the account balance after each next period of time by multiplying again by this expression of 1 plus the interest rate divided by the number of compoundings per year. This leads to an explicit formula for our account balance, A, after t years, where P is the principal or starting amount, R is the interest rate written as a decimal, and K is the number of times per year we compound interest. A consequence of this formula is that if we increase the number of times per year we compound the interest, we get a larger value because we are calculating interest upon previously earned interest. However, this is offset by the fact that we are using a smaller and smaller ratio each time for that calculation. If we boil this down to a very simple example with the principal or starting amount being 1 unit of money, the interest rate being 100%, and the time being only 1 year, we get an interesting expression to explore from a calculus standpoint. If we can go beyond just pennies to as many decimal places as we want, then this expression has what we call a limit as x approaches infinity, and that limit is approximately 2.71828, which are the first few digits of a number we now call e. As far as the finance application, it leads to a formula for continuously compounded interest. We do not make an infinite amount of money if we are compounding interest an infinite number of times per year. Instead, there is a limit to how much we can make, given the way compound interest works. Another example relating more explicitly to calculus involves determining the area under the curve given by f of x equals 1 divided by x from x equals 1 to any other positive x coordinate. Calculus has a way to do this called finding a definite integral. The question then becomes, what x-coordinate will make this area equal exactly 1 unit? Well, it's this magical number again, that approximates as 2.71828. In fact, E shows up over and over in calculus, such as with this summation formula for a special sequence involving factorials. So why is this number called E? First of all, like pi in the square root of 2, it is irrational and cannot be written exactly as a fraction or ratio of integers. Thus we needed a symbol for it. One of the first people to work extensively with this number was a Swiss-German mathematician named Leonhard Euler. This guy was incredible. In his early 30s, he lost vision in one eye, and by the time he was 64, he had gone completely blind. Despite all that, he produced more mathematical works than perhaps any other mathematician ever. In fact, his productivity in some areas of math actually increased after becoming blind. Can you imagine doing all your math completely in your head? I mean math way beyond anything that you or I currently know or can understand. All done in Euler's head and then written down by his scribes. The latest update since this quote shown here is that his collected works now fill more than 80 volumes of books that are each twice as big as any math textbook you've ever been issued. It is actually an accident that Euler used the letter E to describe this quantity we now call Euler's number. It just happened to be the next letter in the alphabet for a list of constants he was working with at the time. He was a very humble man and would perhaps be embarrassed to have it named after him. But we kept the designation and the name Euler's number in honor of this incredible mathematician. And now you can amaze your friends at parties with your memorization of E to 15 decimal places. And have a bit of history trivia memorized also. How, you ask? Well, 2.7 you just better know. It's like everyone knowing that pi is about 3.14. E is about 2.7. Then the next four numbers, 1828, happen to represent the year in which Andrew Jackson was first elected as president. And it wasn't in the same year, of course, but he was elected twice, so another 1828. Then there are the angles of an isosceles right triangle, 45 degrees, 90 degrees, 45 degrees. That's right, you can easily have E memorized to 15 decimal places. 2.718281828459045 and continuing forever. E is a really awesome number that shows up as the natural base to use for exponential functions in calculus, such as here in Euler's identity, which I feel is the most beautiful equation ever, since it relates 5 of the most important constants of the universe in one simple equation. Get used to using E more and more as the base for your exponential functions. In fact, it's the only base we'll really use in calculus.